Okay, so we're on our 10th practice problem. I'm sure you're feeling some relief. You've worked very hard. And we're getting into we should be getting into some really awesome habits. Things should start making more sense. We should start seeing a lot of consistency, some very similar things with these problems that are coming up. Again, if you have not done these problems, you want to go back and try them on your own. Send me an email if you're getting stuck on the setup before you start looking at the video solutions. But let's go ahead and get started. A soccer ball is kicked up into the air at an angle. It takes 23 seconds for the ball to go up and return to the ground. It travels horizontally for 158 meters, and it says, what is the maximum height that it reaches? Okay, so we're old pros at this now. We're not worried. It doesn't give us a lot of information, but we know that that means that we're going to know a bunch of stuff already. So we're going to draw our ground. We're going to draw our ball. We have an initial velocity vector. We're not worried. That's v naught. We know it's at some angle. No problem. That angle we'll call theta. It's going to go on a parabolic trajectory. And they say that the total horizontal distance is, from here to here, that total horizontal distance is 158 meters. And they say it takes 23 seconds to kind of go that entire path. But they want to know this position, this displacement right here at the top. So now we have to think a little bit. They want to know why. Well, we know what VF is here. And we know the time it takes to get to that point. So let's take a look at a couple of these things. First, let's break down our initial velocity vector so that we're in good shape with that one. Oops, not straight. Sorry about that. All right, let's not get sloppy. Let's just do it neat. There we go. So here's theta. So our y component is v naught sine theta. Our x component is v naught cosine of theta. So we can plug those in, v naught cosine theta. We have no acceleration in the x direction, which means my initial and final velocity components in the horizontal direction are the same. I know that this is v naught sine theta, and I know I want to look at this point where my y component of my velocity is 0 meters per second. And we know my acceleration here. So now the question is, what do I do with displacement and time? Well, I certainly don't want to use 158 meters, and I don't want to use 23 seconds because that represents the total path length. But remember that I'm being accelerated at 9.8 meters per second squared, which means the time to get from here to there, from this initial launch position to the maximum vertical displacement, and from the maximum vertical displacement back to the ground is the same because I am hitting it from the ground and landing it on the ground. My elevation, my vertical elevation is the same, launch and landing. So that means my time is half of this. So my time is half of that. Now, ideally you would put in 1/2 of 23 in order to practice not putting in calculated values. But honestly, on this one, if you just half it, I'm not going to get really upset about that. So 1/2 of 23 is, oops, 23 divided by 11.5. So you could put in, I'd be okay, this is the one time where I'm okay with you using quote unquote a calculated value. Because to me, it's not really a calculation. We just kind of know it intuitively that it is 11.5 seconds to the top. And the same thing here. We know that this horizontal displacement will be half. So I'm okay with you putting in 1/2 of 158, or if you prefer, you can just do it in the calculator on this one occasion and put 79 meters. Again, it's not really a calculation. We know this horizontal displacement at the midway point is 79 meters, so I'm okay with that. And we need to find this. And it's a piece of cake because I have everything I could possibly want to in this direction except for the initial velocity. So we need to find the initial velocity. So let's start with x because, again, just like our last problem, I bet you that a tangent is going to pop out here someplace and give us something good to use. So we use x equals v naught x times t, and so I'm going to just move this around. V naught x is equal to x over t, so v naught cosine of theta is equal to 79 over 11.5. And last time I found it very helpful to get this cosine on the other side, so I'm going to do the same thing now. I'm going to take this and I'm going to say 79 divided by 11.5. That gives me 6.8696 divided by cosine of theta. I hope you followed that okay. I calculated this value, which is 6.8696, and then I just brought this cosine over because it worked out well last time that I was going to plug this in for this value up here. I'm going to use the same thing I did last time because it's the easiest formula to kind of deal with. You can use lots of things, but I really want to try to avoid v squared and the ones that have, t squared and all of that stuff. I just don't need to do this. So this is in the y direction. Let me put my subscripts on so I don't get confused. This is 0. So again, I have this value, v naught sine theta, for my y component, and because it has this weirdness in it, let's just put it on the other side. So v naught sine theta, subtract this from both sides, is equal to minus a in the y direction times t. So, and I'm going to just substitute in, since I've already done a problem where we're sort of doing this, I'm just going to kind of jump some steps. So I'm going to take this and I'm going to put it in for v naught as I'm plugging in my values from here. And hopefully I haven't jumped this up too much. So let's plug this all in together, and I'm going to change colors just so it's clear. So I have 6.8696 over cosine of theta times the sine of theta is equal to minus negative 9.8 times 11.5. So I want to remind you that this came out to be the tangent of theta. So the tangent of theta is equal to this value, negative 9.8 times 11.5. Let's just write it over so that I'm not skipping too many steps. Divided by this value here, 6.8696. So theta is equal to the inverse tangent of that mess. 9.8 times 11.5 divided by 6.8696. And I'm running out of space here, so let me just go back down to this page and make sure I've got it all in here. So theta is equal to the inverse tangent of 9.8 times 11.5. Let's just put that little thing in there. Let me go back, make sure I don't copy wrong. 6.8696, 6.8696. Okay, let me just double check again. Remember that I had a negative sign out here and a negative sign in here, which is why I dropped these signs. It's not really that I got rid of them, they canceled out. All right, we're good to go. Let's do the math. So we take the inverse tangent of 9.8 times 11.5, and we divide by 6.8696, and we get theta equal to 86.51. And again, I could carry this out 4 decimal places, 86.5118. But I think we're going to find, because this number right here is very low, we shouldn't end up with a very big rounding error, but I'll do both of them just to make sure. All right, so we go back here just to see what I was dealing with. So recall that V naught was equal to 6.8696 divided by the cosine of theta. So let's do that. So V naught from our x formula was 6.8696 divided by the cosine of theta. So V naught was equal to 6.8696 divided by cosine of cosine of 86.51. So V naught is equal, now let's stick that into our calculator, so 6.8696 divided by the cosine of 86.51. All right, so we get V naught of 112.8488. So V naught is 112.85 meters per second. And let's just double check that this did not cause a rounding error. Let's just poke that in really quick. 6.8696 divided by the cosine of 86.5118 gives me 112.9. And so it's okay. It's a small issue. We would have done 112.9 anyway if we do sig fig. So we're in good shape. I could go either way on this one. These problems get so complicated that as long as we're not truncating up this far, I'm okay. Let's carry it out to 1 or 2 or 3 decimal places and we'll be all right. So our answer here is 112.85 meters per second at 86.51 degrees or better if we were really careful about using this value in here. Then you would have gotten 112.85 meters per 112.9 meters per second at 86.51 degrees. And it is a first quadrant angle. Let's just double check. Indeed, we're here at the first quadrant. Does the number look reasonable? Yeah, it's a long distance that we're going. 158 meters is pretty long. And so we could double check by putting it into another formula and making sure that we get the same answer, because we could solve using anything. We could solve using any of the other formulas and just make sure that we're making sense of these things. Okay, that's it. If you want to see the warm-up done, there's another video for the warm-up, and then there's a list of some extra practice problems if you're interested. All right, good job.